Hi and welcome to the PowerConnect webinar. Today we are going to show you how to get the most out of your moment connections. So you'll be learning today how to use PowerConnect to maximize the resisting moment, and this will be done in 3 steps. The first step is identifying the weakest component. This can be done based on the color graphs or on the detailed results. In the second step, we are going to calculate alternative configurations of the connections by adding, for example, stiffeners, changing end plate or bolt dimensions, and playing around with the bolt positions. And finally, we will have obtained an optimized and of course therefore less expensive connection. And this all within minutes in PowerConnect. So basically we will show you how to interpret the results correctly and how to increase the moment resistance step by step. Now, first of all, improving a connection is not trial and error. It's not adding random stiffening elements and seeing what is happening with the results. No, it is really modifying those elements who will have the most influence so that you only need to add the elements that are really necessary in such a way that the costs stay limited. Now, there is no unique or perfect solution. There are several good configurations possible. We will show you 2 methods or 2 ways to maximize the resisting moment. The first one is a basic, very fast method based on the color graph results in PowerConnect. And within minutes you will have an economic design of your connection. The goal here is to add stiffening elements in the right places. Now the second one is a more advanced one where we go digging deeper into the PowerConnect results. And it's really meant, this one, for fine-tuning the results. And we will also need some background information on the Eurocode calculation method. Our aim here is to not use any stiffener at all. So we really want to know how far we can get without the use of any stiffener. Now, of course, in real life, it will be a mix of both methods. So you will be using sometimes method 1 and at another time you'll be using method 2. To make things a little more hands-on, we'll be using an example. It's a simple moment connection. It's an I-beam to an H column. The bolts are diameter 20 millimeter, the strength class is 8.8, and the welds are 6 millimeter. So let us now go to PowerConnect. So here we have our first example. Now let us start by optimizing the bolt position. So I'm going to double click the bolts and let us now optimize the bolt positions. What does it mean? Well, it means that PowerConnect will try to place the bolts as high as possible, as close as possible to the beam flange and as close as possible to the beam web, taking into account all minimum distances required by Eurocode. Okay, let us now calculate the connection. And currently we have a resisting moment of 57 kN. Now, how can we increase this resisting moment? Well, we have 2 graphs. We have here a graph with the applied moment, but the applied moment is currently 0, so we'll be ignoring this graph. We'll be looking at the other graph, this one over here, and this is the graph with the resisting moment. So this is the 57 put on the connection. And what you see over here is the elements that are most loaded that will have a more red color. So over here, in this case, so the beam web is the most loaded element, is the most critical element of the connection, and it's shown in red. So it will be the first element to fail in the connection right now. So if we want to do something, if we want to increase the resisting moment right now, we need to check out the column web. Yes, there is no point in modifying, for example, the thickness of the end plate. So I will show you. Let us go back to the geometry. I will double click the end plate, and the current thickness of the end plate is CF. Now CF is really a reference to another dimension in our model, and you can see this over here with the BH button. So CF equals the thickness of the column flange. Now I will change this one into, for example, 50 millimeter. So let's go crazy. It's quite a thick end plate, and let's calculate the connection again. And as you can see, our resisting moment is still 57 kilonewton meter. It hasn't changed a thing. Why not? The end plate was not a critical element. So we really need to do something about the column web. Okay. Now I will go back to the geometry, and I will change back the end plate to CF. So this is the thickness of the column flange, which is a very good value to start with. Now, about the column web. What can we do about the column web? Well, you cannot thicken the column web as easy as you can modify the thickness of the end plate, because normally the column web is fixed, so you cannot change it. But there are a few elements you can add to the connection to help the column web. So let's select the column. I'm clicking one time with the right mouse button, and here we have some elements we can add to the connection. So one of the possibilities is a web plate. Another possibility is an upper stiffener or a lower stiffener, and we have, for example, also a diagonal stiffener. So let us start by adding an upper stiffener. Okay. And let us calculate the connection again. Calculate. Now, as you can see, we have now increased the resisting moment. We are now at 79, almost 79 kilonewton meter. And if we look at the color graph, then it's no longer only the column web, but it's also the column flange, the end plate, and the bolts, who are now the critical elements. Who will now fail first? So what are the possibilities right now? Well, we could go on with the column web. So maybe we could add a lower stiffener, or we could try to do something about the bolts. So what could you do about the bolts? You can choose a bigger diameter for the bolts. You could improve the strength class, or you could also add bolt rows. Now for the end plate, you could modify the thickness of the end plate. For the column flange, you could add a backing plate. So many options, many possibilities. Let us simply choose one. So for example, let us add some bolt rows. So we're going back to the geometry right now, double clicking the bolts, adding one bolt row, and optimizing their positions. So with the optimization function, the bolts are already placed high enough, but the optimization function will make sure that the interdistances between the bolts are equal, so that they are equally distributed over the end plates. I'll calculate the connection again, and we are now at 97.7 kilonewton meter. If we are looking at the color graph, well, the bolts are still in red, so is the end plate, the column flange, and the column web. So maybe we could add another bolt row. Let's go back to the geometry, double clicking the bolts, adding another bolt row, and optimizing the positions. Okay, and let's calculate again. And we are now at 104 kilonewton meter. And as you can see, the critical elements are still bolts, end plate, column flange, column web, etc. So maybe we could try to add another bolt row. So going back to the geometry, we're double clicking the bolts, and we're adding another bolt row. And let us now optimize the positions. Now, as you can see, our newly added bolt row is gone. So what does it mean? It means that taking into account all minimum interdistances according to Eurocode, yes, this newly added bolt row cannot be placed over here. So there is not enough space, not enough room for this extra bolt row. So we're a little bit stuck for the bolts right now. Adding another bolt row is no longer an option. However, something we could do over here is maybe changing the strength class of the bolts. So instead of an 8.8, we could use a 10.9. So you can change this over here in the bolt details. So instead of 8.8, we're choosing 10.9, confirming with OK, OK, and let us now calculate the connection again. And we're now at 107 kilonewton meter. So, still, the column web is critical, the column flange is critical, the end plate and the bolts are critical. Let's focus again on the column web, and we could, for example, add a lower stiffener. So I'm returning to the geometry, selecting the column, and let's add a lower stiffener. Calculate it again. We are now at 130, so perfect. Now we still have the column web problem, the bolts problem, the column flange and the end plate problem. What can we do? Well, maybe adding a web plate. So I'm selecting the column and I'm adding a web plate to the model. So let us calculate the connection again, and we are now at 148. And as you can see, the column web is no longer a critical element in our connection. It's even so that the beam is becoming more critical right now. Yes. Now, if you are using a web plate, you should be very, very careful, because the influence of a web plate is very interesting, but you need to respect some minimum distances mentioned in Eurocode. So if you go over here to the detailed results of PowerConnect for our current combination, yes, you can see that Eurocode is requiring some minimum upper and lower lengths for this element. Yes, so the minimum lower length of the web plate is 130 millimeter, so about 120, and the minimum upper length is 53, so almost 60 millimeter. Yes, if you not foresee these minimum lengths in your model, in your connection, you cannot use the positive influence of the web plate. Yes. So I'm returning to the geometry right now, and for the web plate, I'm going to double click it. I'm adding a minimum upper length of 60 and a minimum lower length of 120. And we'll click OK. So, and this is now the correct configuration, the correct way to handle or to use the web plate. If we calculate again, of course, we will have just the same results, being 148. Now, say you have the possibility to make these extensions in the model. Yes, maybe it would also be interesting if you could extend the end plate. So for that reason, just to show you the influence of this extension, we will delete the web plate. We will add it later on, and I will now double click the end plate, and let us go for an upper extension of 75. I will double click the bolts now, and let us optimize the bolt positions again. Click OK, and now we can calculate the connection again with this new added upper extension for the end plate, and we are now at 157 kilonewton meter. And now, as you can see, still column flange, end plate, bolts, column web. So maybe for the end plate, we could thicken the end plate a little bit. So double clicking the end plate, instead of CF, which is the thickness of the column flange, maybe I could use 18 millimeter. Okay. Let's calculate it. And as you can see, the end plate is no longer a critical element, but still the column flanges. And it's not so easy to modify the thickness of the column flange because of the fact that this is all already a fixed parameter, a fixed value. But you could use a stiffening element to modify this or to enhance this. So I'm going to open the dialog to add an element, and the correct element over here is a backing plate. So we'll add a backing plate to the column flange, and I will double click the backing plate, and let us take a look for the bolt throws. So currently the backing plate is going all over only the first two bolt throws, but I want to have that the backing plate is going over all 4 bolt throws. Okay. We'll be calculating the connection again, and we are now at 168. And of course, still the bolts are in red, the column web, so we could add our web plate again and calculate the connection again. Oh yes. And we are now at 194, almost 195 kilonewton meter resisting moment. So we started off with 57, so we now have almost 4 times as much as our starting value of resisting moment. Yes. And as you can see here in our color graph, the beam is becoming critical right now. So this is the point where you should do something about the beam if you want to further increase the resisting moment. However, another option could be, for example, adding a haunch. So we deliberately not have used any haunches until this point because we really wanted to show the influence of these different stiffeners. So for adding a haunch, I'm selecting the beam, and here you can opt for a lower haunch, for example, and then you can double click the bolts and optimize the bolt positions, and you can calculate it. And now we are at 288 kilonewton, which is a lot. So let us now return to the PowerPoint. Let's have a little summary of our example. So we first started out with a resisting moment of 57, and the critical element was the column web. Then we have added an upper stiffener, and we had a resisting moment of 79. We added a bolt throw, so we went to 98. We've added another bolt throw, we ended up with 104. After that, we could not add any more bolt throws, so one of the options was adding a lower stiffener. We also changed the bolt quality to 10.9. Then we have added the web plate. Be careful, of course. Again, if you're using the web plates, please respect the minimum distances required by Eurocode. We have removed the web plate, and we added an upper extension for the end plate. We have modified the thickness of the end plate. We have added a backing plate, and finally we have added the web plate again, and our final value was almost 200 kilonewton meter resisting moment. So that was it for the first method. Now for the second method, the second way, so this is the way you want to follow if you really want to fine-tune the results, if you really need that little extra, but it also takes a little bit more time and also some knowledge about Eurocode. So we'll be starting in the second method with the Eurocode calculation model. Now, say we have a beam column connection. So we will add a normal force, a shear force, and a moment force. What will happen with the connection? Well, something like that. Okay, it's a little bit too much, but you get the idea. So we can distinguish different critical zones in this deformed connection. So over here we have a zone in tension in the column. We also have zone in tension in the beam. We will have zone in compression in the column, and also a zone in compression in the column, and we'll have a zone in shear. Now each of these zones consists of different components, different parts that can fail individually. So for example, in the tension zone, we could have yielding of the column web, yielding of the column flange, yielding of the beam web, yielding of the end plate, bolt failure, weld failure. For the shear zone, we could have shear failure of the column web panel. And for the compression zone, we could have crushing and local buckling of the column web, and crushing and local buckling of the beam web and the beam flange. Now, for each of these components, of these parts, we'll be calculating the resistance, and the resistance is expressed as a maximum tensile force F. And we'll be also calculating a stiffness. This is expressed by the stiffness factor K. Now, we will not focus today on the stiffness, so we can ignore this for the examples today. Now, in Eurocode 3 part 8, this is the part about connections, you can find all kinds of formulas for the calculation of the maximum tensile force F and the stiffness factor K. For our connection in particular, which components or which parts of the connection do we need to check, do we need to verify? Well, first of all, we need to check the column web and shear. And I've also mentioned the section in Eurocode where you can find the formulas. The second one is the column web in compression, the column web in tension, the column flange in bending, the end plate in bending, and the beam flange and web in compression, and finally the beam web in tension. Now, we have made an overview of all these formulas, and on the left-hand side we will place all the formulas for the column, and on the right-hand side we will put all formulas for end plate and the beam side. So the first one to check is the column web and shear, and this is the formula. So what do we see over here? Well, we see the yield strength of the column web. So this is a very simple value. It's a known value. We have the safety factor and we have the shear surface of the column web. Second ones to check is the column flange in bending and the end plate in bending. Now I've grouped them together. Why? Because these checks for the column flange in bending and the end plate in bending are very much alike. There are a lot, like 99% are similarities. So there are 3 formulas to be checked, and you have to take the minimum of all 3. So this is the first one. What do we see over here? Well, it's the thickness of the column flange, the yield strength, safety factor, and some effective length, and an M factor. Now, if you take a look at the end plate in bending, it's just the same formula, except, of course, instead of the thickness of the column flange, we have, of course, here the thickness of the end plate. And instead of the effective length for the column flange, we have an effective length for the end plate. And this is the same really for the second value to be checked. So we have here the thickness of the column flange, the yield strength of the column flange, and here we have the thickness of the end plate and the yield strength of the end plate. So these checks are very, very much alike. Now, the L effective and the M and the N factor, which we don't know, well, they are mentioned in Eurocode 3 part 8, of course, and they depend on the different bolt positions. And you can find formulas to calculate them. What else needs to be checked? Well, we have the column web intention and the beam web intention. And again, these 2 formulas are very similar. So we have the yield strength of the column web, we have the yield strength of the beam web, we have the thickness of the column web, the thickness of the beam web, the B, so an effective width, and this effective width is taken equally as the effective length. Same over here. And the only difference really between these 2 formulas, this of course the safety factor, is this omega factor, which is a reduction factor, and this formula for the omega can be found in Eurocode too. And finally, we'll have the column web in compression and the beam flange and web in compression. So, and here for the column web in compression, you will need to take the minimum of these 2 formulas, and these are very similar to these ones. So we have the yield strength, the thickness of the column web, the effective length, and this is also another K factor which is taken into account. Now, for the calculation of the L effective, so the effective length, Eurocode uses equivalent T-stubs. Now, following components or following parts use this T-stub, so it's the column flange in bending, the column web in tension, the end plate in bending, and the beam web in tension. Now, a T-stub, what is a T-stub? Well, it's a piece of plate representing the flange, and that's a second piece of plate representing the web, and here you can see already how we got the T name. So this is forming a little T, and we need also 1 or more bolt throws with 1 bolt, of course, on each side of the T-web. Now you can recognize these T-stubs all over the connection. If we rotate this element over 90 degrees, well, if we have a beam column connection, you can see a T-stub over here, and this T-stub is consists of the column web together with the column flange and together with 2 bolt throws. You could see another T-stub over here. We have a piece of the beam flange together with a piece of the end plate and 2 bolt throws. Now, you should always consider all possible T-stubs. So we will have to make one with the first bolt throw, and then another one with the second bolt throw, and then another one considering all bolt throws together. And for example, here we have a T-stub with only 1 bolt throw for the column, and for the beam we have a T-stub with a piece of the beam web together with a piece of the end plate. Now, what is so special about these T-stubs? Well, each T-stub has 3 different possible failure modes. The first mode is a complete yielding of the flange. So the flange of the little T-stub will fail first, and the bolts will remain the same. They will not fail first. In a second mode, a second possibility of failure is that the bolts together with the flange will fail. And a third possibility is that only the bolts will fail. So the flange is stronger than the bolts, and the bolts will fail first. Now, mode 1 usually occurs when you have thin plates but strong bolts, and mode 3 will occur when you have thick plates but weaker bolts. Now, you never know in advance which of the three will be determining or which will be decisive, so you need to calculate each of these three modes and take the minimum. So this is in correspondence with the three different tensile forces for the column, flange, and bending, and the end plate in bending. Now, say we have found for each part, for each component, the maximum tensile force. Well, then you have to take the maximum tensile force for each row, taking into account, of course, all the components, and for the calculation of the resisting moment, will be multiplying these tensile forces by the level arm. And that will give us a resisting moment. Now, what should you remember for the resisting moment? Because we have told a lot. Well, as you can see, and it's directly in the formula, so you have a direct influence, the level arm is very, very important to increase the resisting moment. Another thing is, of course, that the maximum tensile force is a minimum of all the different components. So if you want to have a higher resisting moment, so a higher tensile force, you should affect the minimum of all these components. Otherwise, the tensile force will not go up. So if we take a look again at our table with the different formulas, and let us assume that we are not going to focus on the beam part, so only the end plate and the column part. So let's forget the beam formulas. Well, we rearranged a little bit the formulas so that we can get a summary of the influence parameters in these formulas. So we have our different components with the formulas, and now let us see what is influencing these components. Let's start with the bolts. Say we were to edit or to modify the material, so the strength class of the bolts. Which components will be affected? Well, it will be clearly the column, flange, and bending, and the end plate and bending, but only if mode 2 or 3 is critical. If it's mode 1, well, then the material will not have any effect at all. Now, for the diameter of the bolts and the positions of the bolts, well, the column web intention will be affected, the column, flange, and bending, and the end plate and bending. For the end plate, if we change the thickness of the material of the end plate, well, it will be only the last component, so the end plate and bending, who is affected. If we foresee an extension in the compression zone, well, you just have to take my word for it, but it is the column webbing compression, and the maximum value or the maximum influence you can get over there is 2 times the thickness of the end plate. A horizontal stiffener will affect the column webbing compression and the end plate and bending. If you place one in the tension zone, well, the column webbing tension will be affected, as well as the column, flange, and bending. If you add a backing plate, well, it will only have its influence on the column, flange, and bending, and only mode 1 or mode 2. If you would add a web plate, well, it has its positive effect on multiple components, so such as the column webbing shear, the column webbing tension, and the column webbing compression. And finally, adding gussets, haunches, end plates, etc., is useful for any of these components, but simply for the reason that the level arm is increased, so the resisting moment is also being increased. So, and let us now do the same example as before, but following the second method. So I will now open a new file. Okay, so here we have the same connection. First thing that we are going to do is optimizing the bolt positions. So let us double click the bolts and let's optimize the bolt positions. Optimize the bolt positions. Okay, and let's calculate the connection. And of course, we end up with 57 kilonewton meter. Now, if we want to use a second method, we need more information about the results. Yes, so we are going to ask the results per component, per part. So, and what do we see over here? Well, of course, the total moment resistance, we know already that. And we see also for each bolt, which is the restrictive component. So this really means which is the critical component. Yes. So apparently for all of the 2 bolt rows, this is the column web in tension. Now below you will have a list with all the components calculated. So we have indeed the column web in shear, the column web in compression, the compression in beam flange and web, the column flange and bending, the column web in tension, the end plate in bending, and the beam web in tension. Yes. As you can see, bolt row number 1 is taking about 50 kilonewton meter. Where is this value coming from? Well, the column web in tension is critical, so if we take a look at the column web, yes, we see indeed this is 164, and if we take a quick look, we see this is the minimum of all the tensile forces calculated. So the 164 is critical. And if we take a look now at the level arm is 306 millimeter. So if we would now, I'm using the little calculator, so if we would now multiply 164.3 to be exact, and we multiply it by the level arm, I will put this in meter, of course. Well, we're ending up with 50.27, so this is 50.3 kilonewton meter. So this is where this value is coming from. Now, we want to affect or we want to increase the resisting moment, and our critical component is the column web in tension. What do we have to do? Well, I'm returning to the PowerPoint presentation. And here we have the table again. So column web in tension, what are the options? Well, we could add a gusset haunch. No, there are not options. A web plate, well, our goal is to not use any stiffeners. Also, the horizontal stiffener is not an option. So the one thing left is playing with the diameter or the positions of the bolts. So I'm returning to PowerConnect again. And let's go to the geometry. And let us double click the bolts. So playing around with the position of the bolts, what are the options? Well, we could, if I'm selecting this bolt row, we could move the bolts vertically. Yes. But this will mean practically that our level arm will be smaller. It will decrease. Why? Why? Because the bolt positions are now optimized. That means that the bolts are placed as high as possible, as close to the beam flange as possible, taking into account the minimum requirements by Eurocode. So the only way is down, and that is not a good idea because less level arm means less resisting moment. something else we could do is play around with the horizontal positions. So let's try that one. I'm selecting the bolt row and I will move them horizontally and all together. Let's say, well, we'll move by 10 millimeter, maybe 119. Okay. And let us now calculate it. And if we look right now at the critical components, then we see that it's no longer the column web in tension, but it's the column flange and bending. So if we play around with the horizontal positions, these values change. So one is getting lower, another one is getting higher. So I think normally there should be somewhere like optimal value where these three tensile forces should be almost equal. Then we have reached an optimum tensile force. What we see over here, maybe I didn't explain it a few minutes ago. Here we have the maximum tensile force for a T-stub containing only the first bolt row. And here we have the maximum tensile force of a T-stub with only the second bolt row. And here we have the maximum tensile force for a T-stub consisting of both the first and the second bolt row. So the column web has increased in tensile force, the other one has lowered. So let us now try to find a good value for the horizontal distances so that all three are the same. Then we will have the highest resisting moment. Let's return to the geometry and let's all together, yes, moving all together, and we'll put it at 99 millimeter, and let's take a look. And this one is now at 230, 274, 238. I think we can still get a little bit more. So let us now put this at maybe 93 millimeter. Let's calculate it. And right now, all three values are practically the same. So there's still a little difference, but I think it's neglectable. So we have now 238, 242, and 238. So if you really want to optimize the resisting moment, you should make sure, or you should try to have these three values almost the same. Yes. And our resisting moment is now 78.9, almost 79 kilonewton meter. Now, if you remember, in our first method, in our first example, when we added the upper stiffener, we had the same value for resisting moment. So really what we have done here, we have eliminated the use of the horizontal upper stiffener. We don't need it right now. Now, if we take a look at our critical component, because of course we would like to have even more resisting moment. Well, our critical component right now is the end plate in bending. The end plate in bending mode 2. Mode 2 means that, well, it's the end plate that will fail together with the bolts. So it's the flange of the T-stub, which in this case is the end plate itself. So what can we do? Let's return to the PowerPoint. So for the end plate in bending, we could play around with the positions of the bolt. Yes, but that will decrease than this one. So we have to be careful about that. But we could also do something about the thickness or the material of the end plate. Or, of course, another very logical decision would be to add a bolt row. So let us double click in the geometry window the bolts. We're adding a bolt row, optimizing their positions. That is just to distribute them equally, and now I will put them back at 93 interdistance. Okay, so we are now at 97.7 kilonewton meter. So what is our restrictive component? So it's the end plate in bending and it's the column web in compression. So but the end plate in bending, it is still mode 2. So mode 2 means both end plate as well as bolts. So we could try to add another bolt row. Going back to the geometry, double clicking the bolts, adding a bolt row, optimizing positions, place them all together where they should be at 93, like this. Okay, and let's calculate it again. So we are now at 104. Okay, great. Now if we take a look at all the critical components, so we have the end plating bending, okay. And as we know from our previous example, it's no point in adding a fifth bolt row, it doesn't work here. There's not enough space to place them. And the column web in compression, and then for the third bolt row we have the column web in compression, but it's not taking any moment at all. The moment is 0 kilonewton meter. So what does it mean? It means that this bolt row is currently useless. You just can leave it out of your connection. Now you can say, okay, but also bolt row number 4 is not taking on any moment. Yes, that is true, but you should always have one bolt row in the compression zone, and bolt number 4 is in the compression zone, so you should really keep that one. So you cannot leave that one out. But bolt row number 3, you can leave it out. So let's go back to geometry, double click the bolts, selecting the third bolt row, and deleting this one. I'm confirming with OK, and calculate it again. And as you can see, we are still at 104. Now, you might think, oh, but just a few minutes ago, we also had 3 bolt rows, and we had something about 98 kilonewton meter. How is this possible? Well, if we go back again and we take a look at the bolts, then in the previous calculation with the 98 kilonewton meter, the bolts were over here. Yes, at a lower position. This position has a higher level arm, so the resisting moment becomes bigger. Yes. You could even opt to use the minimum optimization function. This will place the bolts as closely together as possible so that you can achieve the highest possible level arm, or the maximum level arm possible. Of course, when you do that, we will need to put the bolts back in their position of 93. Now, this is a very interesting feature to increase the resisting moment. However, you should be careful also. You can use this configuration if you have a moment that is always working in the same direction. What do I mean about that? If your moment is always positive or always negative. For example, if you have a structure with wind loads acting on it, you could have one time under wind pressure load case, you could have a positive moment acting on the structure or acting on this connection, and another time when you have like more suction of the wind, you could have a negative moment. And then in that case, you do not have the same bolt positions for the different cases. If you use this function, the complete optimization, then the bolt distances are always equal. So you have the same position of bolts, you have the same level arm for all the different moment cases, moment load cases. So, and for the bolt positions that we have now, this is perfect if your moment always works in the same direction. So if you always have a positive moment or always a negative moment, then this is perfect. Okay, and let us now calculate it again. And we are now at 106. Why? Because due to the minimum optimization of the bolts can be placed even a little bit higher. Now, and we have still the end plating bending mode 2, so what can we do about that? Well, for example, we could double click the bolts and we could change the bolt strength to 10.9 instead of 8.8. Okay, and okay, let's calculate it again. And we are now, instead of 106.6, we are now at 106.9. And if we do that, we have to be careful, because now the column web in tension is becoming again critical due to the different strength or the modified strength of the bolts. We have another behavior of our different components, so we will have to search for another optimal horizontal distance. So I think maybe a little more outside, maybe 96, like that. Still the column web in tension, maybe a little bit more. 98. 99 probably. So now it is the column flange in bending that is critical, and we are now at 108.8. Now, what can we do about the column flange in bending? Well, really not so much, because of course we cannot change the thickness of the column flange. Now, mode 2 means also that the bolts are critical, but I think we have taken all possible measures for the bolts. So another thing we could do is do something about the column webbing compression. And if we go back now to the PowerPoint, well, for the column webbing compression, the options are quite limited. So basically you need to add a stiffener in most cases, but you can gain a little bit by extending the end plate in the compression zone. So we need to have at least 2 times the thickness of the end plate. So returning to our example, going back to the geometry, let's double click the end plate, and I think our current thickness is CF, and CF is about 14, so we should have something, not the thickness, I'm sorry, we should have an extension of about thickness 30 millimeter. Okay, well, let's now calculate it again, and we are now at 110.3 kilonewton meter. So what else can we do? Well, something that is always helping in every case is, of course, trying to maximize the level arm. So what can we do to increase the level arm? Well, we could extend, going back to the geometry, now we could extend the end plate. On the upper side, for example, 75 millimeter. I'm double clicking these. Let's optimize their distances, and let's place the bolts again at 99, I guess, 99 interdistance horizontally, and let us calculate the connection again. And right now we are at 135.7 kilonewton meter. Now, what else can we do? What can we do right now? Well, if we look at the critical components, the end plate in bending in mode 1, is critical. So mode 1 means that the flange of the T-stub, so in this case the end plate itself, will fill first. What can you do? Well, you can change the thickness or you can change the material. So we will change the thickness. We go back to the geometry. We'll double click the end plate. Now instead of 14, we will use 18. And when we change this thickness, we should also change the lower extension. So we'll have 40. So strictly spoken, we only need 36, but maybe 40 is more easy. Okay, that's calculated. And we are now at 141.9, so almost 142 kilonewton meter. We started off at the in the beginning with 57, so we almost tripled the resisting moment. And our critical component right now is the local tension in the welds. So that is something totally different. And then you should go and check the welds and edit them really. So let us return to the PowerPoint. Now we've also made a table with how you can influence the level arm and how you can try to have these three components, so the column web and tension, the column flange and bending, and the end plate and bending, how you can try to get them equal to each other. And then the bolt resistance, the BT. So if we change the vertical positions and the level arm is affected, for the horizontal positions, well, you can play with the horizontal positions for the three components. If you add a bolt row, well, that's good for the level arm. If you use thinner bolts, it will affect the level arm. How is that? Well, thinner bolts can be placed higher or closer to the flanges of the beam. So it will help a little bit. And then thicker bolts will of course affect the bolt strength, the bolt resistance. And any kind of stiffener will increase the level arm. Now, for our example, well, we started off with the 57 resisting moment. Now the critical elements, or the critical element was the column web and tension. So we have optimized the horizontal distances and we ended up with 79. And the next step, the end plating bending was critical. So, and that was mode 2, so as well as the bolts as the end plate. So we've added the bolt row. Then we have added another bolt row and removed it again. We have changed the end plate thickness. We have foreseen a lower extension of the end plate for helping the column webbing compression. And we also applied the minimum distances of the bolts. So, and you can use this if the moment has always the same orientation. So if it's always negative or always positive. And then we have changed also the bolt quality. We have foreseen an extension of the end plate. Oh, I'm a little too fast right there. And we ended it right there with the optimization according to the second method. So we ended up with 140 kilonewton meter or moment resistance. Now the conclusion of today is that we have shown you two methods to maximize the resisting moment. So the first method was a basic method, which is very fast, and it was based on the color graphs, and the idea was to add the stiffening elements in the right places. Now the second method was also a fast method, but it was a little more advanced, so you needed some background information about the Eurocode. It is based on the detailed component results, and the goal was to not add any stiffening elements at all. So the question was, how far can we get without using any stiffeners? Of course, in real life examples, you will mix both methods and you will use the one that is helpful for you in that case. But we have shown you today that with PowerConnect you can easy and fast, you can calculate alternative configurations of the connections, and you can really reduce the stiffness. You can even avoid them if you play it well, and you know where to do, what to do. So you can really optimize the connection and save money. So, and at this point, I want to thank you for watching our webinar and hope to see you again in the future.